Greetings to all. In this video, we are going to discuss about losses and efficiency of three-phase induction motor. And we are having two major classification in losses. One is constant, that is fixed loss, and another one is called variable loss. And all the iron loss and mechanical losses are called constant loss, and copper and stray load losses are called variable losses, and the no load iron loss also called magnetic or core loss, because iron loss used to happen whenever there is a changes in the magnetic field, especially stator magnetic field, and whereas mechanical loss will happen whenever we are having a mechanical power being developed at the rotor available at the stator. So we used to expect a shaft power for obtaining that mechanical losses, and whereas variable losses, that is like copper and stray load loss, will happen whenever we are having any flow of current through the winding. So we can call iron loss also as a magnetic loss or core loss, and all the variable losses are happening because of the flow of current through the winding. So we can call all the variable loss as electrical loss. And we know at the time of construction itself, we are aware of the material what we are choosing and the purpose of going with the lamination of the particular material. And if there is any changes in the magnetic field, especially at the stator magnetic field, we can expect hysteresis and eddy current losses. And for avoiding eddy current and hysteresis losses, we are going with a specific material for the core type, and we are going for the lamination type of that core. And in mechanical losses, we used to expect windage and friction loss. And if you are going with the slip ring induction motor, there we used to have a brush assembly next to a slip ring. So due to a friction on the brush, we can expect friction loss on the brush, and also we used to have bearing on the other end of the machine, that is frame. So due to a bearing, we used to expect a bearing friction losses. And all the losses like hysteresis, eddy current loss, windage and friction loss is common for even DC machine as well as for AC machine. Whenever we are having a brush, there we can expect a brush friction loss, or we can have a bearing of friction loss. In variable loss, all the copper and stray load losses are happening because of the flow of current to the winding. We used to have two winding, one is armature winding and another one is called field winding. Or we used to have, instead of having a armature winding, we used to have conductors. So on both stator as well as on rotor, we used to have a conducting material, and if there is a flow of current through the conducting material, we can expect I square R, that is copper loss. So both in stator as well as in rotor, we can expect copper losses. And in slip ring induction motor, again on the top of the slip ring, we used to have a brush assembly, and due to that brush contact, we used to get a brush contact, that is it is also a copper loss. So brush contact loss also will happen, that is available only in a slip ring induction motor. And while coming to the stray load loss, it is again due to the flow of current through the winding, and so we can expect the stray load loss at the winding or at the core. So copper stray load loss or core stray load loss will happen under the category of variable losses. So these are all the losses what we have seen in the previous slide, and we can call iron loss also as a core loss or magnetic loss. And all the variable losses, that is copper and stray load loss, are called electrical losses. And we'll see why we are having a iron loss in the machine, that is magnetic loss. From the name itself, we can say it is happening because of the variation in the magnetic field, especially stator magnetic field, because it is the main field flux. So we are talking about the stator field, that is rotating magnetic field. And if there is a changes in the magnetic field, we can expect hysteresis loss in the stator core. And to avoid that alternation, that is changes in the magnetic field, we are going with the selection of high grade silicon steel material. And whereas for avoiding eddy current losses, we are going with the laminated construction of the silicon steel stator core. And these eddy current losses are happening due to the flow of eddy current to the body of the stator core. It's nothing but the leakage current, the flow of leakage current. Because of the leakage current flow, we are having a leakage flux. So whenever we are having a leakage flux, it is mainly because of the leakage current flowing to that. That leakage current is nothing but eddy current. And to avoid that flow of eddy current, we are going for the laminated construction of silicon steel material. So both hysteresis and eddy current losses are having more dependency on supply frequency. So here in stator we are having a synchronous speed. So we can say that the stator speed is nothing but a supply frequency. So we can expect more iron losses in the stator while comparing with rotor, because at rotor, at standstill we used to have a supply frequency, but at the time of running condition, that supply frequency, that is rotor's frequency, is going to have a dependency on the stator supply frequency with the help of a slip. So we can say the frequency of rotor is very much dependent on the supply frequency. So to be more precise, we can say it is having a direct dependency only at the time of standstill, not at the time of running condition. So the iron losses on the rotor is very small. So we are neglecting the iron losses on the rotor at the time of running a condition. So the second type of constant loss is mechanical loss, and windage and friction loss is called mechanical losses. And we know all the friction and windage losses very small. So this is happening due to a speed drop, that is variation on the speed. We are having a windage and frictional losses on the shaft side. And the last one, that is variable loss, is called electrical loss. And due to a flow of current to the winding available on the stator and rotor, we are having and that electrical loss, that is copper loss. We used to call I square R loss as a copper loss. And whenever there is a changes in the load, either it may increase or decrease, and proportionally we can have a variation on the flow of current. So that we are calling all this copper and stray load loss as a variable loss, and it is also called electrical losses. Now we'll see the power flow diagram of a complete induction motor. And here we are on the stator. At the terminal box available at the stator frame, we are having the terminals of stator being connected with the main supply. So we can say the three-phase supply is being connected with the stator. So the input power is we can say it is the stator input, that is the stator power, PS. And once the flow of current to the stator winding, in stator we are having a field winding. So whenever there is a flow of current through the stator field winding, we can expect the creation of flux, that is called RMF. And at the time of flow of current, we are having stator copper loss. Once the supply being connected to the stator field winding, immediately there will be a flow of current. So once first the current will flow, and because of that we are having copper loss. And due to the flow of current to the winding being placed on the stator core, we can expect the creation of flux, that is called RMF. And because of the variation in the flux, we are expecting stator iron loss. Iron loss is nothing but hysteresis and eddy current loss. Hysteresis and eddy current loss. And now after stator copper and iron loss, there will be a stator output, and it is available at the air gap, and this is the air gap. And that stator output is nothing but the input to the rotor. So we can call this stator output or the rotor input as air gap power. And this rotor input, again due to the EMF inducement on the rotor, we are having a flow of current on the rotor. So we used to call that current as I2. And once the flow of current, immediately we can expect I square R loss, that is rotor copper loss. And due to the flow of current in a closed path, we are expecting rotor flux. And due to rotor flux, we can expect iron loss, but at the time of running condition, it is not having a dependency on supply frequency. So we are removing or we are neglecting the rotor iron loss. So next to the flux creation, there will be a creation of force, and due to that we are having a rotation on the rotor. And we can say that a torque being developed, and that torque development we are calling as a mechanical power developed in the rotor. And now the mechanical power being developed at the rotor is being available at the shaft. So from rotor to the shaft we can expect mechanical loss, and this is happening because of the windage as well as friction happening on the bearing as well as on the brush assembly. So at the final output that is available on the shaft is called the shaft power, that is P out. So we can say the electrical input as P in, and the rotor mechanical output, that is shaft output, is called P out. And here we used to call this mechanically developed power as a gross mechanical power. It is a gross mechanical power. And here the shaft power is called a net mechanical power because we have removed the mechanical losses here. So here we are having the inclusion of loss over here. It is a total power, and after removing the mechanical loss from the gross power, we can get net mechanical power. So shaft power is called a net power, and the power developed on the rotor, that is a torque. Due to a torque, the power developed on the rotor is called gross power. So this is about the power flow diagram. So we can write a power balance equation with respect to stator, and we can write power balance with respect to stator and with respect to rotor, and again with respect to shaft. So we can expect three power balance equation. So power balance equation nothing but input should be equal to output plus loss. So with respect to stator, the stator input is PS, that is P in, and the stator output also called as rotor input, that is PR, and we are having stator core and stator copper loss. And this is with respect to stator. Now with respect to rotor, the rotor input is stator output, that is PR, and the rotor output is the mechanical power being developed, and this is called gross mechanical power. And losses are rotor core and rotor copper, and we can remove this rotor core loss due to a less dependency with supply frequency. So we can have only rotor copper loss at the rotor side, and at the shaft the input is the gross mechanical power being developed at the rotor, and the output is the shaft power, and this is the net mechanical power. This is the net mechanical power available at shaft, and losses are mechanical losses. Here the losses is shaft, that is windage and frictional loss. And if we are going to have any variations on the load, we can expect stray losses also. So these are the power balance equation with respect to induction motor. And the input supply, that is electrical supply, we can write as √3 BLIL cos phi. So we are talking about the three-phase supply, there is three-phase input. We can write the input electrical supply as √3 BLIL cos phi. And we know the formula for copper loss, it is I square loss, but here we are talking about three-phase induction motor. So we are going to express copper loss as 3 I square R. And we know the relation between the rotor input, rotor copper loss and rotor output. And we have discussed this at the time of developing torque equation. So we know the ratio, it is 1 is to S is to 1 minus S. So with that we can find the efficiency, and also we can solve the numerical problems related to the losses, that is power flow of a induction motor. So now we'll come to the efficiency of a machine. Here we can find the efficiency of even stator, rotor, and also for the entire motor efficiency. Now we'll start with the rotor efficiency. We know the efficiency is the ratio between the output and input. Since we are talking about rotor efficiency, the rotor output by rotor input is the efficiency for a rotor, and the rotor output is gross mechanical output, and the rotor input is the output of a stator. So we know the gross mechanical output is the 1 minus S times of rotor input. So here we are having rotor input, so we can write this gross mechanical output as 1 minus S times of rotor input. So in denominator we are having rotor input already, so rotor input and rotor input will get cancelled. So on the whole we are having simply 1 minus S, and we can replace the value of slip by means of synchronous speed and rotor speed. We know the formula ns minus n divided by ns, and after simplification we can get the value of rotor efficiency as rotor speed by stator speed. So this is the efficiency for a rotor. Now we'll see the motor efficiency. So motor output by motor input. Stator input is that is electrical input coming to the stator is the motor's input. So the shaft output is the motor's output. So net mechanical output and the stator input is the ratio. It is going to give a motor's entire induction motor's efficiency. We'll see the problem related to this topic, and in the question we are having a number of pole and the type of phase, and the induction motor develops a power. So we can have a power development only at the rotor, so we used to call that as a gross mechanical power. So they have given a gross mechanical power along with mechanical losses with the value of 1.492 kilowatt, and it is having a rotor speed of 950 rpm, and it is having a supply voltage. So we can call this as a induced EMF on the rotor, and we know the relation between the supply voltage, induced EMF on the stator as well as on the rotor. So all are directly proportional. So we can take this voltage as a supply voltage. It is having a frequency, supply frequency of 50 Hertz. And here the power factor value is 0.88. So the question is we have to find the slip until the efficiency. So these are the given data. Now we are going to start with the first question, that is we have to find the value of slip, and we know the formula for slip, and we have to check with the availability of the data for the formula in which we are having two variables, and we have to check for the data regarding to those variables. And here we are having the value of nr, but we have to find the value of ns. So we know the formula for ns, it is 120 f by 120 f by p. So we know the frequency value and the number of pole is 6. So with the help of this formula we are getting the value of synchronous speed, and by substituting the values on the slip formula we can get the value of slip. And again you can check with the range of the slip. For induction motor the range of slip is from 0 to 1, and it is satisfying that range. So we can confirm that it is the induction motor. And second question is we have to find rotor copper loss, and we know the two formula for finding the rotor copper loss. One is from the general formula, that is 3I square R, and another one is from the relationship with the rotor input we can get with the help of a slip. So this S times of rotor input is another formula for finding rotor copper loss. Now we have to check with the availability of the value for the variable. For the first formula we are not having any current value, so we can go with the second formula, that is S times rotor input. And the first thing is we have to find the rotor input, and by using the mechanical power along with the slip value we can find the rotor input, and at last we can find the rotor copper loss. And last one is total input. So total input is nothing but the stator input, and we know the power balance equation at the stator. Stator input is equal to rotor input plus stator losses. And here we are having the rotor input as 23.55 and the stator losses have been given, and we can get the stator input, that is total input to the machine. And last one is efficiency, and they are asking about the motor efficiency. So the formula is net mechanical output, that is shaft output divided by stator input, and we are not having any net mechanical output value. So from the power balance equation with respect to shaft we can write the value of gross mechanical power, that is input minus loss will give the output. So from that we can find the efficiency of the induction motor. So until now we have discussed about what are the types of losses available in the three-phase induction motor, and also how we can form a power balance equation for stator, rotor and then at the shaft, and how we are having the relation with the slip with rotor input, rotor copper loss and the rotor's output. So with based on those we have derived a value of efficiency for rotor as well as for the motor, and based on those concepts, and we have now discussed about one problem and how to choose the formula for finding the value of a particular parameter. So thank you.